What's the most used man-made material on Earth? I'll give you the answer. Concrete. This is the Concrete Logic Podcast. Have you ever stopped to think about the sidewalks, driveways, bridges, or the buildings around you? They're all made from concrete. So why don't we discuss it more? In each episode of Concrete Logic, we'll explore a unique concrete-related topic with the help of industry professionals shaping the trade's future. We'll talk with suppliers, contractors, architects, engineers, specialists, and even proponents of competing materials. We'll get their views on concrete and their visions for its future. So get ready to mix things up with Concrete Logic, where we turn the spotlight on the material that's everywhere but often overlooked. This is the Concrete Logic Podcast. And now, here's your host, Seth Tandit.
Welcome to another episode of the Concrete Logic Podcast, and today I have Dan McCoy back. He is going to talk to us, or with us, about aging concrete and how we responsibly treat and maintain concrete. But before we get started, real quick, just to remind you all how you can support the podcast. You can do one of three things, or you could do all three things. One is share the podcast with a colleague or a coworker that's in the industry or interested in the industry. Definitely want to share it with the younger folks that are coming up in construction and tell them how cool it is to be in the concrete business. Be a specialist, don't be a generalist. The second thing you can do is you go to concretelogicpodcast.com, and there's a couple ways you can reach out to me, send me a message. So at the top, there's a contact button. You click on that and it sends me like an email, or in the bottom right-hand corner, if you're like me, you rather talk than type. There's a little microphone there. You click on that, and it's like, if you click on that, it's like leaving me a voicemail. And again, I'm just looking for topic or guest suggestions, because this podcast is for you. So tell me what you want to hear on the podcast. And then the last way is on the same homepage of concretelogicpodcast.com. There's a donation button. And I want to thank, we've had a handful of folks send in donations. Those are greatly appreciated, but that's what that donation button's for. So you go on there and you click on it, smash it, whatever you want to call it, push that button, give any amount, and it helps me make the podcast better. I don't know if you guys noticed lately, but so folks have donated, and what I did is I went out and I hired somebody to do the intro and the outro. So, that's the things you'll see. The more you give to the show, I throw it right back in. I'm not using it to feed my kids. I'm putting it right back into the show for you guys. So with that, Dan, let's talk about aging concrete. We were talking before we hit record about how we should treat it or heal it versus maybe just sealing over the top of it. And you were talking about you're doing something that you think nobody else is doing in Indiana. So let's tell us a little bit about what you're doing.
Well, thanks for having me on again, and I love the new intro. It's fantastic. It sounds like we're on a national radio show. I love it. But I love coming on here and getting my concrete geek and my engineer on, because I try to talk at home with my wife. And I'm telling you what, guys, if you're listening to this, your wife does not want to hear about it. It's one of those things. I start talking, I get that glazed, look, and I'm just like, this is fascinating. And she goes, whatever you say. So yes, thanks for having me back on, because it allows me to get my geek on a little bit, and talk about some of the things that we're doing or trying to change in infrastructure, the way we look at things. And I think, if the dedicated listeners will remember, one of our last shows, I think we talked about, the aging infrastructure problem. We specifically talked about bridges, but aging infrastructure in general, and how we went from, the National Highway Transportation Act by Eisenhower to build all this wonderful infrastructure that we use for commerce every day. You know, it's a big driver of how we get and do things. If you have anything, odds are it was delivered to you on the final stage by a truck. And it got there using our international highway system or other local municipality routes. There's a few private tollways out there, but a lot of it, the vast majority, is public transportation in the means of you provide the wheels, we provide the road. And as I noted before, you know, even with current infrastructure standards and current infrastructure bills, we're not replacing that infrastructure in a manner that will be to replace that infrastructure as much as needed. So we're having an aging infrastructure right now. We're in it. We're dealing with our if there was one of those elderly care facilities for infrastructure, that's what we'd be running right now. And instead of producing newer or replacing that infrastructure, we're piecemealing it and replacing what we can, and we're trying to extend the life of our existing infrastructure in the United States. I have faith. We'll get there. Necessity breeds dollars, and once it gets bad enough, it'll eventually happen. But you need several $1 trillion to invest in new infrastructure. And as that happens, or before that happens, you have to take care of what you've got. You've got to maintain these assets so that you keep health and welfare up and alive and working for people. And one of the things we've done in Indiana is I have the pleasure as a contractor to be on kind of like I call it R.O. McCoy, special operations.
Oh, I like that name. That's cool.
Special operations, because there are contracts in INDOT, and I'm not sure if other states, I'm sure they do to some extent, but we get basically this blank contract, and it's called an IDIQ contract, and it's IDIQ stands for indefinite description, indefinite quantity. So you're given a base bid on items of here's kind of what we're going to do. Here's the items you might see. Or like the current one is, it's based on labor hours, equipment hours, material. And then you bid a markup to those against a competitive bid process. And then, they choose who the lowest bidder is. And for the last 5 years, it's been us, because it's been one of those things that is really fun to experiment with new things on. Because you're dealing with smaller, more local issues that I think you could broadcast and turn into larger issues, just like what we're doing today. So one of the things we deal with are those projects that meet a specific requirement. Like I said, the Federal Highway has a list, and they use AASHTO to do it with their bridge inspection, that goes through a rating system. And then what that structure is rated depends on what funds it gets for the type of construction it gets. If it's rated extremely poor, then it gets put to the top of the list for replacement. Or if it's rated somewhat high, it doesn't get as many maintenance dollars, even though there may be something else wrong that needs to be fixed. And that's the scenario that we're in, mainly with IDIQ. Because if it was worse, it would already be in contract or in design to be ready to go to contract. So what you have are these assets that are of a particular age or have particular problems that are detrimental to the future of the structure without requiring a five alarm bell emergency on it. And you say, well, how can we get this structure to last a little bit longer, a couple more years? That's one of the things that most of these projects have been about. We notice these problems. We can't do anything about these problems through capital funding and real bidding to do them, but we have this extra money to go attack those and extend the life of that a little bit. And many of these have been superstructure, substructure issues, stuff that people don't necessarily see too often, but it definitely precipitates the need to reconstruct or replace that asset in the future. So a lot of these structures are we'll say penciled in for replacement in 2029, 2030, 2032. But we just got to get them there, and we want to keep that asset alive and viable for that time to get it there. And one of the ways, we did this, and I got to give full props to Dr. Belkowitz here, being the nanosilica expert that he is. He came up with this product. Eddystone is the name of it. And it's a really brilliant idea that comes from, why don't we take those already underlying chemicals that are causing problems and use them to our benefit in aging concrete? So things like carbonation, things like, especially in bridges or culverts where you see a lot of these nasty phosphates and chlorides, calciums, and all this other stuff that inevitably attack. Parking garages are one that I love the most, because you think that's an interior concrete, but then you bring the outside in, right? So in the Midwest here, if you're driving in on a winter day, you're going through these treated roadways that have all this salt and grime, and it begins to stick to the underbelly of your car, and then you get to work and you go in a parking garage and it's all nice and dry in there, and you go into work, and while you're sitting there in work, all these ice clumps are just dropping off, just like in your garage. I'm sure every one of you that lives in the Midwest or the upper North know that, you can tell where you park your car in your garage, because you can begin to see that deterioration of concrete where all this stuff starts to drop down, and starts to eat away at the concrete, all these nasties. And when you go to a parking garage, it's great. Now I know everybody listening to the show looks at concrete a different way than normal people, like we just discussed. But once you hear this from me, you're going to start going to these parking spots, and you're going to start looking at your garage floor and go, oh, wow, when my car's not there, I know exactly where I park. I can see an outline. I can see where the garage door comes down and traps those chlorides in there. Just wait. You're going to look. And it's like, how do we deal with that? And in the old days in infrastructure, one of the ways to do it was to use old days. They're still using it. So it's to use the sealer healers that are out there. And what those are more like an epoxy based type thing. So but think about what you're doing when you're doing that. Now, you see cracks or voids, and then you use like an epoxy injection, or you use a very viscous or a very low viscosity epoxy to hopefully go in there and try to fill in these cracks, and then it cures in its own way. But it's not a cementitious material in the effect of what does it do to the concrete. It essentially covers the concrete and then hardens. So what you're doing is you're placing a stopping point there. You're covering it up, but there's blunt cracking that takes place underneath that. And years later, eventually, when you go back, and you can ask any concrete guy, let's say you've been around for 20 years, you on the first couple of years, you went and applied this, and then 5 or 6 years later, you go back and you sound it, and you notice that it sounds pretty hollow in there, even after all this is going on. It's because that crack has continued propagating underneath the surface. You may not see it, but it eventually forms and starts to pop out. And, the folks at E5 and Dr. John, who have forgotten more about nanosilica chemicals than I can even speak to, came up with this solution to say, well, what if we could turn all these nasties in concrete into something good for the concrete that actually heals the concrete? So, and that's what was initially found with self-healing concrete. Was over several wet dry cycles, it began to form hydrogels, and those hydrogels promoted CSH growth, which is the glue for concrete. And that's why you see a lot of these, even with the internal cures and the liquid fly ash, you see this increased hydration up to a year out. I think in one of your last podcasts, I think they talked about lightweight aggregate and the benefits of internal curing using lightweight aggregate is the way that pore solution stores that water and then releases it over time, and you end up with high strength concrete 100 years later. And what's happening is, normally, I say in the old days, but if you're still using standard concrete, what you're getting is you're finding that you're really only hydrating about 70% of that cement, right? And the rest just ends up being really expensive fine aggregate in there. And what the nanosilica and the internal cure with the lightweight aggregate does, because it's real porous and it holds water real well, is it releases over time. It releases that water over time, and it hydrates more and more of that unhydrated cement that you had initially when you mixed your concrete in the fresh properties. And I remember I had a professor in college, and it was Captain Meeks. I'll never forget it. He went to the U.S. Naval Academy, and he was a concrete geek, man. That's what he lived for. Matter of fact, he was from Virginia, and that's where his professional license was from. But I remember him with that Southern accent saying, "Dan, concrete kills forever. It kills forever." And it's true. As long as you keep adding moisture to it, it just keeps curing and curing and curing. The old wives' tale, it's not even a wives' tale, but the old wives' tale about the Hoover Dam, it's continuing to cure. It's continuing to cure time and time again as more wet and dry cycles begin. You hydrate that unhydrated cement particle as you're going. And this, in aging, it's like, how can we do that to an aging concrete, right? Because we've got all these older concretes that we know still have, as Warren Buffett says, when he's looking for maybe not a good stock, but a good for right now stock, he calls it the cigar theory, and I love cigars, but he says, maybe you look around and on the ground, you find a cigar that somebody's left, and it's got one good puff in it, and you want to take advantage of that one good free puff. Well, that's kind of what we're doing with aged concrete and how we're treating it with these nanosilicas, is we're taking this, and it's got this unhydrated cement particle, but then it's always got these nasties in it. How do we use these together? And that's where the solution comes into. It's just the delivery method happens to be nanosilica. So you place this in a surface saturated dry condition, and what it does is it's like if you view a crack as a cut on your skin, it's an antibiotic, right? What it does is it goes into the crack, or it goes into the open pores. Keep in mind that nanosilicas are incredibly small. They're 1,000 times smaller than a cement particle on a micro scale, or on a nanoscale, 1,000 times smaller. So these voids seem really big to a nanoparticle. And it goes in there, but there's other nasties that are in those pores too. The chlorides, the sodiums, iron oxides. It's got all these nasty things. And what it does is it breaks down that nanosilica, and instead of pushing away from each other with electromagnetism, it causes them to come together and stack. And then what that does then is it purges the bad stuff and collects the water. And then it saves that water for hydration for the unhydrated cement using a hydrogel process.
And what is a hydrogel? You've said it a couple times.
So a hydrogel, and now don't get me wrong, you need to talk to the chemical expert on this, which we all know was Dr. John. And I'm so tired of throwing things his way, but he's done it for 20 years, so this is like old hat to him.
Yeah.
But when we say hydrogels, we specifically mean the gels that form in concrete. One of these, there are bad hydrogels too. It's any Spaceball fan out there will tell you there's two sides to every Schwartz. He's got the upside, I got the downside.
That's two podcast episodes that you've referenced Spaceballs.
Ironically, working in the concrete industry is a lot like being in Spaceballs.
Oh boy.
So the bad Schwartz in this case is the cancer of concrete, right? We've got
ASR.
So we've got the alkali silica reaction, which is a bad hydrogel, right? It begins to expand in there. It creates these pressures that we don't want. Because it accepts the bad chemicals and begins to expand, causing crack blunting and all this other stuff. But the good stuff with the nanosilicas forms not the same hydrogel, but a like hydrogel. And it's just like it sounds, hydrogel. And what that gel does is it becomes harder and harder over time, not harder than the concrete, but eventually promotes that CSH growth while purging the bad stuff out. So things like carbonation that we have with aged concrete, it takes advantage of that differential in pH. As the pH comes down, it's alkali susceptible, and then it takes those nasties and begins to purge them out, but it also breaks down itself to collect water, and then the water is saved in the hydrogel, and it begins to promote that calcium silicate hydroxide reaction. So that's the glue of concrete, the CSH of concrete. And
so it's if you're looking at a crack of just a V of a crack, it's bridging the two sides of the crack, right?
Better yet, it's coating all the way down and into the crack, and then it finds that crack blunting and relieves that pressure that would be propagating a crack.
Okay.
And it pulls the nasties out of it, creates that hydrogel, and then at the bottom of the crack, it begins to form CSH, essentially rehealing the concrete. Versus
sorry to interrupt you. Versus the traditional way is if you were to treat a crack, is routing or chipping away the bad concrete and then shoving epoxy down there.
Right. Because what you're trying to do is you're trying to, in that essence, you're trying to stop crack propagation by filling it with something that is going to fill a void. That's essentially what you're doing, is filling the void so that it stops that. But it's those epoxies, and don't get me wrong, I still think on surface treatment, if you've got some early age cracking, one of the best things to do. Now there are other nanosilicas out there that you can place on that early age cracking that will promote this as well. Notice I said silica, not silicates. There's a difference. Because those form gels too. They just, over time, they need to be reapplied. They begin to break down like a silicone gel would.
Like a sealer.
Right. They need to be reapplied. But the other one, you're playing with the chemistry of the cement matrix to actually foster and grow new concrete, or a hardened paste. Let's put it that way. You're not growing new concrete. You're growing more of a hardened paste using the hydrogels. So that is one of the, and I realized, so the other thing that's really nice about nanosilicas is they love water, right? And so what I've discovered is, when you go in for structural patching, and usually let's say we're high strength structural patching. So when I mean high strength, I'm not talking like a UHPC like Bill Coolidge makes, but more so of, I've got a pretty small patch to do on a pretty significant member, like a beam that maybe sees a lot of shear stress. But over time in our joining system, it's taken a lot of waters and a lot of salts, and it begins to break down the end bearing of that concrete. And so you want to strengthen that up. Maybe the rest of the beam's good. As a matter of fact, it probably is, but maybe you have some end debonding in the strands. And one of the things you carefully want to do is support that member and then take away all the bad stuff, chip it out just like you would a structural patch, and put that back in. Well, what I would do, and what I do, is place the nanosilica in there, and it takes all that bad stuff and begins to create these hydrogels immediately. And then I take a high strength patch over it, like a Sika patch or anything, any name brand patch that you want to put out there. And if you want to throw in some fiber reinforcement or carbon fiber reinforcement in there for high strength fiber patching, then that's all part of the process. But what I like is you apply the Neosporin, the antibiotic, to it, and then you place the patch back over it. And what you see is increased bond strength between the newer patch and the old concrete.
Yeah, patch probably performs better.
Yeah, well, it lasts longer.
Yeah.
Right? That's what you're going for. You're going for the longevity. So you're restoring the strength as best you can, because nothing's better than a perfect member anyway. You're just trying to hold it in place and keep it alive for another couple of years, and keep that asset viable. So when you use this, the Eddystone product on aged concrete, it takes advantage of the fact that you've got a lowering pH due to carbonation or due to some of these phosphates or these chlorides coming in, and it takes advantage of that. And the more you give it and the more wet dry cycles it goes through, the harder and better it gets. And the more propagation of CSH that you see. And then you end up with, just like we do with the nanosilica concrete treated today in the mix, you're going to end up with, not necessarily all around, but in that area, you're going to end up with taking advantage of not 70%, you've got 30% of those unhydrated cement particles left. You begin to hydrate more and more of those unhydrated cement particles. And, you end up with, if you core it in several years at that location, what you're going to find is a greater population of hydrated cement in that area, which is everything positive that you wanted to do in the first place.
Right. Huh.
It's all fun stuff, right?
Yeah. Well, it makes a lot of sense. I guess if you just look at it, utilizing the chemicals that are in there that you don't want in there and use them for good is basically what's happening, right?
Yes. Yeah. And that's essentially what you're doing. You're using the reaction between that nanosilica and its chemical makeup and how it's made. Now, there's 1,000,001 different ways to make a nanosilica. I think we've covered that before. There's good ways and bad ways to make nanosilica. They're not all created equal. That's my note for the day. And the other ones that we talk about are patented processes, and they're very specific in how you can manufacture, and that it is a manufactured product. Once it goes through the facility and it comes out being exactly what the user wants, depending on what they're going to do with it. And they're used everywhere, from ink pens to wastewater treatment plants, the stuff that you use every day. But as far as being used in concrete, it's just fairly recent.
Yeah. How long have you been doing this process where you've been applying the nanosilica before you're doing your repair?
Oh, 2 years. 2 years.
And how do you go back and determine that you're getting the results that you want?
So this is an interesting case study that we did. There was an asset within INDOT that we had actually built. We had actually built in 2000, I think, 99, 2000, somewhere around there. They were expanding the highway system on I-69 and adding, replacing pavement. And there was an old abandoned railroad that the new highway or the replaced highway was going to go over. But since it was an abandoned railroad, why should we replace that bridge when it's a bridge over nothing, essentially? So what they wanted to do, INDOT, what they wanted to do was just basically tear out the bridge, which we did, and then fill it back in, and a standard earth bank, because it wasn't crossing a waterway, it was crossing an asset to the railroad that was no longer in use. Track had been removed. It was just railroad right away that they were done with. And ironically enough, there was one property owner that owned property on both sides of the highway. And he said, whoa, I like that access. I like being able to go from one property to the other with all of my equipment, with all of my valued assets. And it was an auction company. And if anybody's ever, heard of Auburn, Indiana, it's one of the Auburn Court Duesenberg Festival, and the Auburn auction. But that's how they would move these Duesenbergs and high dollar, we're talking $1 million cars, from the museum on one side to the auction floor on the other. It's a huge property. And so he said, wait a minute. What if he says, what if I throw in some money and you guys build us a tunnel? And we said, well, that's interesting. Let's see what INDOT thinks. INDOT saw that and says, well, if you pay for it, and then you manage it afterwards, then we're more than fine with that being an asset under our asset, which was the highway. And we built that in 2000, and then covered it up. So it's essentially a tunnel that's 16 feet by 14 feet by, 300 foot long.
Oh, wow.
Yeah. Oh yeah, it's on a skew. So, it's a pretty good skew. And what we used segmental cast in place concrete pieces as we went. So like a moving form system, just like with a tunnel. And we built that and then tore down the bridge and then backfilled around it. So essentially it's a large, dry cast in place culvert, right? Mm-hmm. But it signifies one of the problems that we have. This is why it was unique. It signifies one of the problems that we have with our aging infrastructure is not all of the elements or the structures that cross highways or go underneath highways are bridges, right? We still have to be able to move water. And you have a lot of these smaller structures, whether it's a reinforced concrete pipe or whether it's a true culvert or a precast culvert. The way you put it in is you can't do it all at one time. They're so big. You end up with cold joints in there. And then you try to protect those joints as well as you can. But where you see the beginnings of that asset falling apart, or at least the trouble, is at the cold joints, right? If you can eliminate a cold joint in something that's meant to be continuous, you're eliminating a big headache for the future, right? Mm-hmm. So you try to eliminate those as much as possible. But in this tunnel, we did these in 40-foot segments. So we've got like seven cold joints in there, and it's covered up by about 12 feet of earth-packed material and clay, backfilled with like a B-barrow, and then a B-barrow is like a really, really fine, coarse to fine sand. But that's what you normally see on the drawings, and in the commercial world, I'm sure you see in some of your sections that you don't really care about so much, where you see earth on the other side, it says engineered fill, mm-hmm. right? So that engineered fill, when we talk about it as engineers in the geotechnical sense, all that means is it's soil that I know what it is.
Yeah. Okay.
We know its moisture content. We know its angle of repose. We know that it's a drainable material, so it's not going to build hydrostatic pressure. That's what we backfill it with. But again, I said the key word, drainable material, right? What does that mean? It means that all the waters and chlorides and salts that come in from up top eventually come through and then go around the structure to drain out and away. Mm-hmm. But what you have over this, large flat structure is you eventually have pooling that takes place up there around these cold joints. And eventually that moisture builds up and starts to work its way through. And then you have, keep in mind, a culvert's open to air on the top, even if you've got water running through, it's open to air on the top. And it's going to go through freeze-thaw cycles, just like anything else underneath. Mm-hmm. So you have moisture coming down through this crack. It freeze-thaws, pops, freeze-thaw, pop. And you begin to see this joint breaking out, and it begins to look pretty ugly. And that was one of the problems with this asset. And luckily enough, we got word that something had gone wrong in the process of whoever was responsible to take care of it. The property owner said 20 years ago that he would take care of it. He was supposed to sign a legal document saying that he would. Evidently, nobody followed through on INDOT. It was lost in limbo. INDOT still maintains this structure to this day. They never wanted to. They never wanted it. And finally, the asset manager in the area and the program director was just like, well, this is just a liability for us. We've got active traffic going overhead. We don't need it to be a problem. We're just going to fill it in. And I said, whoa, wait a minute. I got an idea. And the idea is everything in Indiana, just like most of the rest of the country, is going to, we're installing trail networks like nobody's business for walking trails and biking trails, give you that park atmosphere, that sense of community. And I said, whoa, one of the biggest benefits in a trail system is separating vehicular traffic from pedestrian traffic and bike traffic, especially in an interstate system. Uh-huh. So you have very few crossings of that type along an interstate highway. And I said, I don't think we want to lose this. I think, as a matter of fact, these old abandoned railways are perfect places to put these trails. That's what they've been doing for most of the time. They take these old abandoned right away because nothing's ever been put on it because the railroad owns everything forever. And they put a walking trail on it then. So it's fairly clear of utilities. It's fairly clear of buildings over a couple hundred years. So it's an easy access, just wide enough to put in a nice walking trail. And that's when the existing property owner and a couple other trail organizations got together and says, yes, we would like to save this asset and we would like to take care of it. And I said, I think that it's something that I could turn into an experiment, which is exactly what I did with the hydrogels. So we went in there, and we basically said, well, if you're going to fill it up anyway, or if it's no use to you, let me core it, make some Swiss cheese, and get some samples out of it, and see what we're doing. So that's exactly what we did. And we went in there, and to get to this is a long way to get to your answer of your question is, where have you used it before and how do you see it working?
Uh-huh.
And we said, okay, we're going to split it right down the middle. We're going to treat this half of the tunnel and we're not going to treat this half of the tunnel.
Okay.
And the joints look fairly uniform, as in to the point where they looked horrible, like really bad. I mean, you've got oxidation, stalactites, bad stuff, right? You can see that water just leaking and pools on the floor of where that water's draining through, like a percolator in a coffee cup, right? It's just coming through. And we said, and I sent those pictures to Dr. John, and I said, so is this the stuff that you were talking about? You want to try this? And he starts frothing at the mouth. And he's like, oh, these are great. This is fantastic. And I'm like, I've never heard anybody look at a crack this bad and say, this is fantastic. So we took some water samples. And this was for a later product that actually has to deal with soil stabilization, using nanoparticles. But, when you take that water and you send it in, you can do it the easy way, right? There's a free kit you can go get at Home Depot to tell you whether your drinking water is good or not, right? So you can go get this and you can collect this water and then you send it off to them. And then they'll call you back and they'll recommend products or a water softening system, to clean your drinking water. And I got a panicked phone call from the third-party agency that tests the water. And, I put all my information on there and I'd sent the water sample off and I get this call back. It's frantic. And it goes, Mr. McCoy. And I said, yeah. I've been waiting on a call from you guys, a water testing agency. She goes, you're not drinking this water, are you? And I go, no, I'm not drinking it. I'm just seeing what's there. They're like, oh boy, that's good. I would recommend looking somewhere else because there is a lot of nasty stuff in this water.
Uh-huh.
I said, oh, that's interesting. Could you send me the report? They sent the report. Of course, it's everything. Take a glass of water and collect the runoff from your local highway in the middle of winter. That's what you had, right?
Mm-hmm.
You've got a lot of nasty chlorides and phosphates on there. Everything that you put there to prevent ice, everything that's running off the vehicles. It's definitely something you don't want to drink, but it's also all the bad stuff in concrete that we don't like to add to it. And that's where it was coming from. It was running right through there. So it had these nasty chemicals. And the best part is we have an unlimited supply of these nasty chemicals that are just coming down every year, through that filtration system. And the best way to tackle it was to say, okay, well, we're going to go up and we're going to sound it. So we did. We went up and sounded at the side we were going to treat it, and we knocked out all the loose stuff that was going to be a hazard, and it would just fall out in chunks. And then we would clean it using high pressure pressure washer water nozzle. Okay. Something generates around 3,000, 3,500 psi to clean the surface off, get everything out, get it surface saturated dry because it's key to have that water. And then we placed the nanosilica up there in a very fine mist. And there's no health hazards associated, which a lot of other stuff you see health hazards associated with. But this one, you just place this on here. And then I thought, well, this will be a long-term experiment. Let's see what happens. We came back the next morning to do more of the other sides, and you could actually see the hydrogels already forming in the crack. And that's what was amazing to me. It was just absolutely fantastic. I was thinking about this the other day, and sight or picture say 1,000 words. If you say that a nanosilica does something or any product does something, but someone can't see it. And even if you've got all the empirical data to prove that it's happening, they still think, nah, I don't know what's going on here. But way back in the day, if you showed someone a camera and said, this takes pictures of you, and nobody believed it, and you took a picture of them, and then you showed them the picture, then they go, oh, let's just take pictures of you. I get it. You've sold me. Seeing is believing. It's one of those things. But you just can't do that on the nanoscale and the micro scale of the stuff that we want to happen. But in this essence, that's what you could see is those hydrogels forming. And the more water that was coming down, it had taken that water on the one side of the tunnel from the night before. The other side was still leaking and percolating, and this side was just accepting all that moisture and all those nasties and forming those hydrogels, which then was going to propagate and make, via CSH, was going to rebuild and heal our concrete. So now, obviously, we wanted to do a lot more than that. We were just stopping there to see what would happen. So in a good world, what you would do is you would take something like that and you would incorporate it into your patching material. And then you would also do something to repair that joint of where you do have copious amounts of water coming in. You still don't need, when I say you need water, you don't need that much water as far as healing over time. But it does everything to help, and it's all the positive things. So that was my first real aha moment of, wow, this is really working. This is fantastic. I can see using this in a lot of places. And then you have an easier time understanding how it works with maybe surfaces that are that old or older. This concrete was only 20 years old, but a lot of times we're dealing with concrete that was built in the 1930s and 1940s. And maybe you don't have really bad cracking because it's been pretty sealed from the environment as far as, hardcore exposure. But you still have carbonation taking place, and you have those tiny little holes, everything that you can take advantage of that pH beginning to lower. Once you can take advantage of that and start replacing all those nasties with some good hydrogels, you're going to reactivate the unhydrated cement particles that are in there, begin to grow some really self-healing concrete. Cost was the other issue. It was absolutely fantastic. I don't know if any of you are out there listening in the Midwest, if you can find someone that can do vertical or overhead concrete structural patching for less than $100 a square foot, you're an absolute genius, right? I mean, if you can do it less than that, it's unbelievable, because then you think, God, that can't be that expensive. Well, it is. And I've tried more than one way to skin a cat, and it just takes that long. And it takes, the right kind of mixture with the cement paste and the patch to get it right, to stay there. And then if it's a deep patch, you have to add it in layers. And you're an absolute genius. But I was able to apply this stuff, labor and everything, and purchase the product. And I was able to do it for like $10 to $12 a square foot. So when you think about being able to prevent, maybe you don't want it to get that far. When you want to be able to prevent something from like this happening, where you have these big, long, horrible looking concrete structures, which are sometimes fun to look at because you think, man, this asset really did its job. It's really done its job over the years. But if you can do things like that and apply it, then, I used it on an IDIQ project where we had to repair some beams that were the same way. And then we had patches falling on pier walls that would come off. They were old patches that were done 15 years ago. And you end up inevitably going back and placing the same patch. Well, it's because you can do as much as you want with surface prep, but you're still going to have that cold joint around that patch. And it's still going to permeate and leave that moisture to come in, even with those nasties. And you're going to have that propagation that occurs on a micro level, builds up these intense pressures. And if you can treat that prior, or treat it as you see it with, something that's going to be an antibiotical cream to put on the concrete, then now you're talking about a true sealer healer, right? In the essence of, you're using the bad stuff to create more of the good stuff, purge out the bad, create these hydrogels to make the good. And that's the stuff that we've been playing with. It's fairly exciting So I know I've done so much talking. I am so sorry. You should probably.
That's what you're supposed to do when you come on here. I keep telling people that like that. They say, I feel like I'm talking too much. I was like, that's why you're here. You're here to talk.
Right. Right. But, we'll come back to one of my other loves. And of course, if you guys know, you know, if you're listening now, you know that I'm a nuclear geek too. And one of the reasons that I'm fascinated about nuclear engineering and nuclear science is it's amazing how much we know about that process. This didn't come along until Enrico Fermi started this thing in the 30s, and people said, okay, I can equals MC squared. I can turn matter into energy, with the right chemicals. And then they studied it and studied it and studied it. And now in a reactor, you can have nuclear engineers that know that if I run a reactor for this long at this concentration with the rods this close together, I'm producing this many atoms of cesium and this much plutonium. And I know exactly what isotope it is and how long the decay time is, right? We know that I get excited about this because we know so much about it, and it was created, basically invented in the 1930s and 40s. We've had concrete for thousands of years, and we still don't know what's going on a molecular level as it starts to happen and what we're producing. It just blows my mind. And here we use it everywhere and all the time. And we know literally less about what's going on in that nucleation than what's going on in a nuclear reactor right now.
Mm-hmm. Yeah, I don't understand why people don't. Yeah. See, that you just sold a concrete career right there.
Well, right. I mean, it's such a valuable material. I've heard Dr. Lay explain it 1,000 times to 1,000 different people. It's the most used man-made material on the planet. It's what we do. It's what we make. It's very cost effective for what you get out of it. And why not take care of it? Why not create new ways to reuse it? And that's where the magic of sustainability happens. How can we get these assets to last longer? Well, we can design them better right now. We can use better materials right now that are meant for longevity and sustainability to get that asset that was normally meant to last 75 years to get another 25 years out of it minimum, get 100 years out of it, 120 years out of it, depending on the climate and other things like that. But if you can do that and plan that well ahead, that's where you're making your environmental impact. If you can prevent doing all this and spending all this extra time and money in the future, then that's what you're doing. And people tell me all the time, well, you're a contractor and you're an engineer. Aren't you kind of like, self-fulfilling prophecy? You're kind of killing your job in the future if you do it too well. And I'm like, no, that saves more money for the new infrastructure that we need.
Yeah.
And I'll build that too, so if we can do that, it's going to be for the better. It's going to be for the better.
Nope. I agree. Yeah. It's, what we need to be doing. I mean, we keep beating the drum saying that concrete's the most sustainable material on earth, but just not winning them all, Dan.
Yeah,
well,
if they all believed this, it wouldn't be very much fun.
That's true too.
It forces us to do things like this and really do the testing that's required of why this is working and what's happening, it's a good thing. It's to be questioned on this stuff. I love it because, the results speak for themselves when you're, especially in the future. It just, I remember Dr. John asked me one time, what's your ideal concrete mix? And, and maybe I'm going to, for fun, let's flip it on him, folks. Seth, what is your ideal concrete mix?
Oh my gosh. The one that makes money.
I like that.
Yeah.
I do. I like that. That because we've looked at so much, right? Look at all the stuff we can do. You had Steel like Bill Coolidge on before, who I love, and he talks about ultra high performance concrete, which in his world, he cringes a little bit when you say concrete because it's a composite, right? It's his life. It's a goodie bag of materials that is unlike any other, even different other UHPCs. That's one form of concrete. And then we've got the lightweight that you discussed in your last episode, which we've used in bridge decks before, which we do in hospital floors mainly for weight reduction and for the fire rating code. And you know, it's difficult to pump sometimes, but treated right, you can do it all the time. And there's other benefits to using the lightweight aggregate, like the internal cure mechanism that basically Dr. Jason Weiss came up with 20 years ago, about, hey, this is how internal cure is working with a lightweight porous aggregate. There's so much that we can do and so much more to learn. That's what's exciting. You know, by the time it becomes, you know, more prevalent in the future, you know, things like carbon nanotubes, you know, will become more prevalent, and the price will come down on those, and you can begin to make some higher modulus concrete with lower compressive strengths. And you know, you can begin using less of the really high dollar coarse aggregate, you know, around. I mean, there's so much cool stuff that you can do with concrete. It's not, you just call a ready mix company and say, I want concrete, and all concrete's created equal. The dirty little secret is that even if you ordered the same concrete 20 yards and you get 2 10-yard loads, they're not the same.
Yeah.
That's the dirty little secret, because they can't be the same. They can be within a standard deviation, but they're not going to be the same.
Yeah. Yeah. We could talk about that for another hour, but I think we should wrap it up on your healing. Like you said, to address this the right way, so we're not keep on spending money on frivolous repairs, is to actually address the cause of the crack, right? And I'm not saying take away the methacrylates or the epoxies. I think that's an acceptable method for covering up and concealing cracks. I'm saying we should do something to the crack beforehand. Yeah, then all that stuff, yeah, all the epoxies and sealers and all that will just perform that much better. So, exactly. Yeah. All right. Exactly. Right. There's a lot of stuff to do but hey, I am so happy to be here. Thanks for having me back. Yeah. I was supposed to give you some grief. I think Dr. Belkowitz and maybe even, was it Bill Cooley? I think there were a bunch of them that were saying that if you've been on the show, you get a free t-shirt. Free t-shirt. You got to be on the show 15 times, I think, to get a free t-shirt. My God. I like that. Yeah, there you go. I keep moving the goalposts every time somebody asks about it. So that's absolutely fine. Maybe you just need a couple of us to get together and just make you a t-shirt and just randomly send it to you. And when you open it up, you'll say, that is the coolest t-shirt I've ever seen. It's cool. Yeah, we'll figure it out. But all right, Dan. Well, I appreciate you coming on the show as always. I always have fun with our conversations, and we'll get you back on for sure. And folks, until next time, let's keep it concrete.
Thanks for joining us for another episode of the Concrete Logic Podcast. If you got value from the show, here's how you can provide value back to support the show. Visit concretelogicpodcast.com and click the donate button to send value back. All dollar amounts are truly appreciated. And now, to close out the show, here's Mike Dunton.
Ring, ring, that alarm always sings couple hours before the sun comes up. Open up the side, put some diesel in the lights and wait till the trucks roll up. Yeah, this ain't how most folks live their lives. Dripping in sweat, working overtime. But while they're tying their ties for their 9 to 5s, we're out here changing these skylines with wood, iron, and mud. We work hard for $1, give thanks to the Lord above. Never make a man do something you can't prove. Hard work calls for a drink or two. Expect more, it's written in our blood. With wood, iron, and mud. city, from the Lone Star heat to the woods of the Georgia pine. Good old boys and girls who ain't afraid of getting dirty for a clean time. And if you want to see the fire in a grown man's eyes beneath the hot summer sun, find the wild-eyed boys clocking days and nights, working hard to get that job done with wood, iron, and mud. We work hard for $1, give thanks to the Lord above. The color of our collars ain't white or blue, we're all gray collar through and through. Expect more, it's written